Because there's no way he's surviving this.
Wait, where's that coming from?
Okay, so here's how this week is going to play out. So we got projectile motion, which is going to be 3 days, today, tomorrow, and Wednesday. Then we're going to have a midterm final on Friday, so that means we're going to review on Thursday. Midterm final is going to be mostly multiple choice, vast majority of it. There's going to be like one or two like big problems to work out at the end. But the vast majority of the test is going to be multiple choice, okay? So that's going to be on Friday, that's going to be worth 20% of your grade. So we've got, like I said, 3 days of projectile motion, a day of review, midterm on Friday. So that's how that will play out. And like I said, your grades are updated. Everything that I have is in there, and you can see exactly where you're at. If you want to decide, like on that forces test, if you want to, like I said, there's that option if you want to retake that forces test, you can. Just come in before, like probably after school, and do that. But if you're got a good enough grade, and like I said, the finals were 20%, so pretty much your grade to a certain degree is set in stone. But if that's, for some of you, that might make a difference on that forces test. So, like I said, you have all the information so you can make that decision. You know exactly what your grades are, right, as of right now. Okay, so the cool thing about projectile motion is that we don't have to learn any new formulas. We're just going to repackage the ones that we have. Okay? Now, with projectile motion, there's two generally broad classifications of projectile motion. And today we're going to do what I call lemming problems. Does anybody know what lemmings are famous for?
Suicide.
Suicide. Doing what?
Mass suicide.
Doing what?
Just following each other in a line off a cliff.
Off a cliff. Okay? So according to the legend, so lemmings, here's the cliffs of Dover in England. Okay?
So sad.
And the lemmings run along and they jump to their death.
Why?
Okay?
Because they're dumb rats.
Yes. So
They can't control
it's
it.
actually really not, it isn't really, it doesn't happen all that often, but this is just what I call lemming problems.
They probably
Okay?
can't control it.
So with lemming problems, here's what's going to happen. You're going to
Negative.
go running along, and then you're going to begin to fall. Okay? The other option is like a golf ball, where you go into ground to ground. And that's a situation where you're going to go like this, okay?
Like a ballistic missile.
So those are the two broad classifications of problems. Now, here's the other mantra that you will hear again and again and again. It's kind of like the ads for Vegas. What happens in Vegas stays in Vegas, okay? So here's what's going to be different, is that we're going to be dealing with two different axes. A horizontal axis, an x-axis, and a vertical axis, okay? So here's your mantra, is that what happens in the x stays in the x, okay? And what happens in the y stays in the y. They're completely independent of each other, okay? So we're going to have horizontal motion, it's going to be cool. We're going to have vertical motion, it's going to be cool. Nary the two shall meet, okay? What happens in the x stays in the x, what happens in the y stays in the y. Now, here's the most important assumption that we're going to make with lemming problems, okay? Is that your initial vertical velocity, VYO, kind of sounds like the name of a horrible physics game, VYOs, okay? We're going to assume that that initial vertical velocity is going to be 0. It's going to go running off a cliff. We're not going to shoot it up in the air. We're not going to shoot it down. It's going to go boom, off like this, okay? Now, obviously, on a ground-to-ground problem, your initial vertical velocity is going to be some positive number. Otherwise, it's not going to get off the ground, okay? So, lemmings, they're simple. They're just going to go, we're just going to shoot that out. This one's going to be, the ground-to-ground is going to be more complicated because now you're going to have acceleration. Now, the other key assumption that's going to happen in both of these is that we're going to assume that the acceleration in the x direction is going to be 0 meters per second squared. Okay, so what we're going to assume is that if I take, I don't know, yonder penguin with a laser, I don't know why it does, but this is the assumption that we're going to make. So I'm going to assume that when I shoot that laser out, like that, it works. Okay?
Analysis.
So that when that laser gets shot out like this, that when that thing goes flying through the air, we're going to assume that there is no forces acting in the X direction. Okay? We're going to assume that the inertia is going to have it maintain that velocity. So there's no horizontal forces. Now, in reality, because we have an atmosphere, which is a good thing, okay? In reality, there is going to be some horizontal acceleration. But that gets real tricky because then you get into, like if you've ever played soccer in Kansas, okay, there's a big difference between you kicking that soccer ball with the wind versus you kicking that soccer ball into the wind, okay? You get into like drag coefficients and what's the surface of the ball and the horizontal accelerations and all this weird stuff. It just muddies the water, okay? Yeah, clearly if I take like a wadded up piece of tissue paper and I try and throw it to Cassidy, it's not going to get there, okay? But if I take a golf ball and I throw it to Angelina, it will get there, okay? So in reality, there is horizontal acceleration. But that's just really going to make life complicated, and we're just going to leave that out. Because that's kind of the great thing about physics is like, oh, it complicates it, we'll just ignore it, okay? The same thing is true if you talk about like vertical acceleration when you drop something. Oh, we'll use 9.8 meters per second squared. That's an idealized value in a vacuum, okay? In reality, things don't accelerate 9.8 meters per second squared the entire time, but it's a nice mathematical model. Okay, so when this thing gets launched, okay? When this thing gets launched, okay? So that's going to go flying off like this. So when that thing is launched, the only velocity that it's going to have is in the horizontal direction. And then we're going to assume that that's not going to change, okay? So horizontally, we're going to use this. R equals Vx time. R is going to be the range. That's your horizontal distance, okay? So that's how far it's going to go. Okay? This is your Vx, horizontal velocity, and this is time. Now, you're looking at it going, ooh, that's a new equation. We've never seen that before. Okay? Yes, you have. You've seen distance equals velocity times time. What's the only time you can use distance equals velocity times time? Well, there's no acceleration. Guess what? Horizontally, there's no acceleration. So all R equals Vx time is just distance equals velocity times time. Okay? That's all it is. Okay? It's not a big deal. Don't flip out. Oh, it's a new equation. No, it's not. Okay? Guess what? If you were to draw the horizontal velocity versus time graph, what's that going to look like? So when this thing gets launched, what's that going to look like? I know that's so non-dramatic. Okay? What's that going to look like?
Like kind of arched down.
It's going to be a horizontal line, right? We're going to assume the horizontal velocity is constant. Okay? And it's just going to go across like this. But guess what? When you find that area, what are you finding? Oh, that's going to be the range. That's how far it's going to go. Okay? So that's why I said there aren't new equations. It's just, you know, we're just going to repackage it. Now, vertically, that's a whole other story. So here's what I want you to imagine. Okay. Okay. Now, I want you to pretend that none of this is there. You don't know. We have not talked about projectile motion. We have done nothing. Okay? We are getting ready for the acceleration test. And I'm going to hold a golf ball up from a height of 2 meters, and I'm going to drop it. Okay? So, what are some things that I can find about that ball right at the point of impact? So, here's this ball. It's a height of 2 meters. Jamie, what'd you say?
Final velocity.
We can find the velocity, final velocity using what? We know a distance, but we don't know time.
2
Huh?
2ax. No.
No.
No, I don't know time. That equation. Ah! I can go v squared equals v naught squared plus 2ad, right? Okay, equation we've used 100 times. What's my initial velocity? 0, okay? So v is going to equal the square root of 2, your equation has it as x. So somebody take 2 times, and what's the acceleration going to be? Negative 9.8 meters per second squared. And the distance is technically going to be negative 2 meters. So somebody take 4 times 9.8 and then the square root of that. 6 point something, I think.
6.26.
6.26 meters per second. Okay? And I just want to know how fast it's going, so I'm not worrying about making it negative. Technically it is, but I just want a number for now. Okay? So it's going to be traveling 6.26 meters per second. Now, I want to figure out how long it's going to take, but I don't want to use that number, because if that number is wrong, then the next calculation is going to be wrong. So, the wall, how can I find the time without using the 6.26 and only using the height and my acceleration? I'll give you a hint. It involves 1/2 AT squared.
Okay, yeah.
Yeah.
We don't have our
Yeah,
numbers out.
bad.
Yeah.
How about distance equals v naught t plus 1/2 AT squared? How about that? How about that?
That's good.
It's good?
Yeah.
So I'll see if I can continue on the roll, right? I'm going to take 2d and divide it by a, and then take the square root of that and get my time, right? Okay. You're going to use this equation a lot with projectile motion. Embrace it. Become one with it. Okay. So somebody take 2 times 2 meters and divide that by g, and then take the square root of that. It's less than 1.
0.64.
0.64 seconds. Okay? All right, 0.64 seconds. Cool. Now, let's talk about this. To do any of these calculations, okay, look at this calculation here. What's the only information that I had to give you to find the velocity of that ball when it landed? What's the 2 bits of information I had to give you?
The
Acceleration and distance.
The acceleration and how far it fell, right? That's it. That's it. Nothing else. I didn't have to tell you that it was a top flight 1 golf ball. I didn't have to tell you that it was white. I didn't have to tell you that, oh, it bounces pretty good when it lands, okay? But most importantly, what else did I not give you that we've talked about? Mass. I didn't give you the mass. You know why?
Not important.
Doesn't matter, okay? You can't plug mass into those equations if you try. So the only thing, and this is going to be important, the only thing that determines how long that ball is in the air or how fast it's going is 2 things. The acceleration due to gravity and how far it falls. That is it. Nothing else, okay? Nothing else. Now, with that said, I got this handy dandy little gizmo, okay? And what's going to happen is that it's got a plunger, right? And we'll talk about springs later when we get into energy. But I'm going to do work, and I'm going to pull this back, and I'm going to compress that spring. And when I flip it up, whoop, because Mother Nature hates potential energy, so it likes kinetic energy. They got crossways at some point over Instagram, Snapchat, something, okay? They don't like each other. I'm going to pull this back, hold that. So when I flip that, it's going to take one of these marbles, and it's going to shoot it out like this. And the other one,
Shoot it at me.
no, the other one, it's got like a hole in it, and it will halt, and it will be on the back, and then when I launch it, it's just going to fall, okay? So what I'm going to do, and this is about 2 meters, so can you guys get that camera to spin? So here's what's going to happen. I'm going to have this up here like this. I'm going to have one with a hole back here. And then I'm going to launch this one, okay? So I'm going to flip that. One's going to get shot out and become a projectile. It's going to have a horizontal velocity going out like this.
Is he gonna hit that ball?
The other one's just going to fall straight down. So here's the $1,000,000 question. Which one's going to land first? The one that gets shot out, because it's going to have more velocity, so it shouldn't be in the air as long.
Land on the ground or land on anything?
No, just hit the ground. Okay? So, option number 1, that's going to land first because it's starting with a velocity. Okay? Option number 2, this one's going to land first because it's just going to fall straight down. This one's got to travel further, so it's going to be in the air longer because this one has to travel a greater distance. Okay? So that's option number 2. Option number 3, gravity doesn't matter which what's happening, and they're both going to land at the same time. Okay? So we've got the launch one's going to hit first, the drop one's going to hit first, or they're both going to hit at the same time. So, how many vote the one that's launched is going to hit first? Okay? What about the one that's dropped is going to hit first? Huh. Everybody's in agreement they're going to hit at the same time. Okay, so who's going to be the class spokesman that's going to represent all of you? Cassidy? Okay, you got voted. So you're going to speak for the whole class.
Right
Why? Why are they going to hit at the same time?
Other than I've seen this before, gravity.
That's valid.
Yeah.
Hey, past experience is valid, girl.
They're both falling the same distance, and gravity's the same for both of them, so it's not going to change it.
Now, I want to pick up on one thing. You say they're both going to fall the same distance.
They're starting at like the same height.
Okay? So are they going to fall the same vertical distance? But they're not going to travel the same horizontal
The same
distance.
vertical distance.
They're going to travel the same vertical distance. Okay. So, either all of you are right, and I've taught you well, or this is going to be an absolute train wreck, and I'm just going to quit teaching. Okay? There's a lot riding on this experiment. Okay? Been teaching here since '93. Burkamp quit today. Why? His entire class voted wrong.
We're done.
All right. I'm ready. 3, 2, 1. Ooh.
What was that? It sounded pretty much like the exact same time.
Yeah, that's kind of what I'm hoping too. Because I really didn't want to have to quit. I didn't want to have to go to pot still. Hey, starting the second English, you got to find a new physics teacher. I'll stay here till Friday, but then I'm out. So he'd be like, "What?" Okay.
You're a smart one.
Now here's the deal. And Cassidy was right. Okay, she gave a wonderful explanation beyond the fact that she's seen it done. Okay. But more importantly, she understood the science behind it. So look at this calculation of time. Okay? This is where you go back to what is a factor and what is not a factor. Okay? So what's the only thing that determined the amount of time that thing was going to be in the air?
Gravity.
The gravitational acceleration and
Vertical distance.
how far it fell, the vertical distance, right? The fact that it was launched horizontally, was that a factor in that calculation at all?
No.
Didn't make any difference. Okay? Did it make any difference that one had a hole in it and the other one didn't? Not a factor. Mass is not a factor. You know why? Doesn't matter. Now, there is one huge thing that's important. Okay, and this is subtle, but it's very, very important. When they're both launched, okay, like this, and then this one falls straight down. This has a certain Vx, but here's what's important, and this is of vital importance. What is common is that they both have an initial vertical velocity of 0. Because once you simplify that to time equals the square root of 2d over g, that is not like a big dog equation. Okay? It's not, this equation is not on your equation sheet. What is on your equation sheet is the idea that distance equals v naught t plus 1/2 at squared. So you can only solve for 2d over g if the initial velocity is 0. But again, That's an initial vertical velocity, and it goes back to, and harkens back to this whole idea. What happens in the x stays in the x. What happens in the y stays in the y. Okay? So, yes, it was launched with a horizontal velocity. It's great, did, fantastic. But that's a horizontal velocity. So what you have to be careful of, when you look at that equation, that distance equals v naught t plus 1/2 at squared, if you're going to use g as your acceleration, that velocity then has to be the vertical velocity, not the horizontal velocity. Because again, if you look at this, and this is where this all goes full picture. Horizontally, there's no acceleration. Distance equals velocity times time. Oh, that's that range equation that we just talked about. So this works horizontally. Oh, if there's no acceleration horizontally, which there isn't, because we're assuming that the inertia is going to maintain that velocity, that part goes away. Range equals Vx time. Vertically, we're assuming that there is no vertical velocity. This is my gravitational acceleration. This is going to be my vertical distance. Okay? So that's why I said, here's your mantra. What happens in the x stays in the x. So in the x direction, this is just distance equals velocity times time. Okay? And this is going to be that horizontal distance. Vertically, this is going to be y. This is going to be 0, and you're going to have 1/2 gt squared. Okay? So keep them separate. Okay? X, y, marry the two shall meet. Got that? Good? Great? Fantastic. So that's actually one of the debates of, like if you shoot a gun horizontally and you drop a bullet at the same time, which one hits the ground? Okay? And unless it's something weird, like they will both hit at the same time, when that doesn't happen, and we'll talk about this when we get into like when something's actually in orbit. Like if you're on top of a mountain, because the Earth is curved, and don't tell me it's not. So since the Earth is curved, on an extreme case, the one that's shot will actually take longer to hit the ground because the Earth is going to curve out from underneath it. Okay? So in an extreme case, and that's an extreme case, okay? In an extreme case, the one that's shot will take longer, but you have to take the curvature of the Earth into account. And that has to be going really, really fast and travel a long way for that to happen. So we don't have to worry about that. But here's the cool thing about putting something into orbit. If you get it going fast enough, it'll just continuously be in a state of free fall around the Earth. Okay? And it will just never hit the Earth because the Earth is curving out from underneath it. And that's what happens when you launch things into orbit. So if I could throw, because if you think about it, if I throw this ball like this, okay, it's going to travel a certain distance. The faster I throw it, the further it's going to go. So imagine we could go outside. This would be like the ultimate physics demo. I could take the ball and I could throw it, okay? And the Earth, it takes about an hour and a half or something to complete one orbit. So at the beginning of the class, let's say at 1 o'clock, we'd go outside. It's like, okay, class, I'm going to throw this golf ball, okay? And then an hour and a half later, we're going to go back out. I'm going to put my hand up, and then I'm going to catch it because as it comes back and completes one orbit, okay? But obviously, I'd have to throw it really fast, and the ball would burn up in the atmosphere because it would instantly get vaporized because of the friction. But it would be a really cool demo to do. Don't get me wrong. Okay. Now, I have said, it happens in the x, stays in the x, it happens in the y, stays in the y. But there is a point where we can merge these two ideas together. So let's say that when we launched that marble, it traveled 2 meters vertically, okay, so that was my y distance. And let's say that it landed 3 meters away, okay? So that's going to be my range or my horizontal distance. So this thing was launched like this. So what I want to find, knowing that range equals Vx time, so Eli, I know that it traveled 3 meters because that's how far it landed from the base, okay? the time that it was in the air is what we found up here, which was what, 0.64 seconds, okay? That's 0.64 seconds. So I know how far it went, okay? So it traveled out here, 3 meters, then hit the ground. So I know my Vx. I know it takes 0.64 seconds to fall, and that's going to be the same for both of them. So Eli, it traveled 3 meters and it took 0.64 seconds to do that. So how can I find my Vx?
You just divide by the time.
Fantastic, okay? So if I take 3 meters, so somebody take 3 meters and divide that by 0.64 seconds.
4.6.
So I'll call it 4.7 meters per second, okay? So what that means is that that marble, when it was launched, it traveled at 4.7 meters per second. Now, as it falls through the air with the greatest of ease, what's going to happen to that 4.7 meters per second?
Nothing.
Absolutely nothing is going to change about it. Why?
It's not accelerating.
It's not accelerating. We are assuming that if you remember back to like that LIM lab when you would fire like the side engines, and that's the only time we said it accelerated because on the moon we said there's no atmosphere, okay, or aliens or anything like that. That's the assumption that we're going to make here. That that velocity of that marble is only going to change at that point of impact. After it gets launched, there's no horizontal forces, there's no acceleration, it's going to stay constant. So as this thing falls through the air, that's not going to change. Okay? That's going to stay the same. That's going to be easy. So if you were to draw the velocity time graph horizontally, that would just be a horizontal line at 4.7 meters per second. Okay? Straight across. Boom. There you go. Now, vertically, what's going to happen to the velocity?
It's gonna increase.
That's going to increase. So here's the deal. When you look at this path, like this, horizontally, what's my acceleration vector going to look like? Do not make this difficult.
0.
0. There is no horizontal acceleration vector. Okay, there's nothing to draw. Is there going to be a vertical acceleration vector?
Yes.
Yes. Okay. And what's that vertical acceleration going to be?
Gravity.
So negative 9.8 meters per second squared. As it falls, listen to me very carefully, Porter Salisbury. As it falls, what happens to the value of that acceleration vector? Does it get bigger, smaller, or stay the same?
It's gonna stay the same.
Fantastic. Okay? That's not going to change. And we're going to assume that it's not going to change because we're going to assume, like Jamie said, that gravity is a pretty consistent force. Okay? Since we have a pretty consistent force, hey, we're going to have a pretty consistent acceleration. Now, in reality, there's going to be some, especially with our atmosphere, right? There's going to be some drag to it. In reality, that acceleration vector, in reality, actually becomes smaller as it falls faster because it collides with more oxygen and nitrogen molecules. But for no farther than we're going to go, it's just going to stay the same. Vertically, does my velocity change? Yes. Okay? Yes.
Yes.
So vertically, what's my initial velocity?
0.
Yeah, Vy naught, Vy yo. If you want to sound like cool, like you're in a physics game, Vy yo, you can do like flashing little gang signs or whatever. That's going to be 0 meters per second. Okay? Nothing's going to happen. But is it going to pick up vertical speed? Yeah. So that vertical velocity is going to get bigger and bigger and bigger. Now, when it lands, okay, and this is where you have to get the terminology right when you talk about projectile motion. When it lands, we can talk about the speed of the ball when it lands. So when that ball lands, it's going to have a horizontal velocity. What was our horizontal velocity? 4.7 meters per second. It's going to have a vertical velocity of, what was our vertical velocity? 6.26. Okay? Okay? So when it lands, it has two components. a vertical component of 6.26 and a horizontal component of 4.7. So, are these vector quantities?
Yes.
Yes. Can we find the resultant of these if we draw them tip to tail? Yes. And that resultant is going to tell you the actual speed of the ball when it lands. So, I'm going to take this. Take this. And I'm going to move it over here. Oh, that is not what I want. Move this over here.
Is this angular momentum?
And then I'm going to find that hypotenuse. Somebody get out your calculators and take 4.7 squared plus 6.26 squared and then get me that value.
7.83.
7 point what?
83.
So call it 7.8 meters per second. So here's what that means, okay? Imagine that you could be in the ground with a little radar gun, okay? And as that ball is falling towards you, your radar gun is pointing at the ball. And right before it hits the ground, your radar gun would be reading 7.8 meters per second, because that's how fast it would be going right at that point. So when you talk about speed, okay, when you talk about the speed of a projectile, you're talking about the resultant of the x and y components, okay? So that's how fast it's actually going through the air. Now, if you had your radar gun, right at that point that I shot that out, what would your radar gun be reading?
0 or
No. This is the one that shot out.
4.7.
It'd just be reading 4.7 meters per second, because that's the only velocity that it has, right? Then, as it goes through the air, your vertical velocity is going to get bigger and bigger and bigger. So what's going to happen is that you're going to tilt that resultant vector further and further and further down. Not because, and this is important, that trajectory is going to get more and more vertical. Not because your Vx is getting smaller, but it's because your Vy is getting bigger. So as that Vy gets bigger and bigger and bigger, it's going to pull that hypotenuse further and further and further to the vertical. Okay, so initially it's all Vx. Then, and that Vx doesn't change, but as your Vy gets bigger, it's going to get more of a downward trajectory to it. Okay? Got the idea. Now, let's play the what if game. We're going to go back to the beginning. Okay? Back to the beginning. And there's two ways you can do this, smash mouth physics or the more elegant approach. Okay? So here's what I want to do. Instead of launching it from a height of 2 meters, I want to launch it from a height of 4 meters. Okay? So what's going to happen to the amount of time it's in the air? So help me God, if any of you say the word change, I'm going to walk out that door and never come back. Or it's going to be different, Mr. Brickham. Okay? So, I hate that word. Okay,
it's going to increase.
I can live with that. I can live with increase. Okay?
Increase means something.
It does. Change? Okay. So, some people just like the smash mouth of physics approach. Oh, instead of 2 meters, I'm going to put in 4 meters. Now, so does it seem reasonable that if I drop the ball from twice the height, it should take twice the amount of time?
Yes.
Seems reasonable, right? If it was a linear relationship between distance and time. Okay? So, but here's the problem. When you look at time, there's that radical sign there. Oh, it's underneath the radical. Oh, boy. So since it's underneath the radical, do you think there's a straight relationship of like if I double the height, I'm going to double the time?
It's like 1
Yes, bad. Okay? Now, so one option is that we do smash mouth physics. We just crunch numbers. Okay? So we're going to take, so somebody take 2 times 4 meters, because it's going to fall twice as far, divided by 9.8 meters per second squared, and just give me that raw number.
8.85.
What?
8.8. Wait.
There is no way on God's green
Sorry.
earth.
I'm looking.
There is no way on God's green
I was
earth.
doing the final.
It's like, wow, that's a long time. 1 Mississippi, 2 Mississippi, 3.
0.9.
Exactly?
0.903.
Okay, 0.90 seconds. Okay? Right? Now, our initial time at 2 meters was, what was the initial time at 2 meters? 0.6?
0.64.
Yeah, that's right, 0.64. So, clearly, we didn't double the time. Because if we had doubled the time, what would have been, it would have been like 1.28 seconds. Okay? So we didn't double the time even though we doubled the height. It's like, oh man, sucks. What can we do though? But this is where you go with the elegant approach to it. So the initial calculation was time was the square root of 2x over g, right? So that was my initial time. So this is going to be more important as we get into things that are more and more complicated. So then my due time, we're going to call that t prime. Okay, so this is going to be like the new set of conditions. So that's going to be 2 times 2x over g. Now, Isaac, since this is underneath the radical, can I write that as the square root of 2 times 2x over g? Is that cool? Right? So I'll multiply it. I can separate that out.
Yeah.
Now, out of curiosity, somebody take the square root of 2, just give me that number, and multiply that times 0.64.
It's like almost 0.905.
You get basically the exact same number.
That's
Okay.
42.
So your time doesn't double because it's underneath the radical. It's going to increase by the square root of 2. So here's the more elegant approach. And this is the one that I hope you begin to embrace more and more as we get into more and more complicated equations. Okay? Is that I hope that you begin to have that ability to go, I don't need to smash mouth physics. I'm going to look at a more elegant approach. Okay? To be able to say, okay, I'm going to double that. That's going to be underneath the radical. It's going to increase by the square root of 2. Because here's where it's more applicable. Let's say that I had quadrupled the height. Okay? So it went from 2 times 4x over g. So if I quadrupled the height, then it would double. If I wanted to triple the time, okay, if I wanted to triple the time,
Times 3. Times 9.
I'd increase it by a factor of 9, right? Okay? Because then I'd have the square root of 9 underneath the radical, which would give me 3. So that's why if you can embrace the more elegant approach, it allows you to see a lot further than you can if you're just plugging numbers into a machine. Okay, now let's take that same approach. If I double the height and that velocity was 2ax, if I double my height, what's going to happen to that velocity? Will it also double?
No.
No. What's it going to increase by?
Probably the square root of 2.
Maybe the square root of 2 again. Because then v prime, or that was v, my bad, go away. So v prime would be the square root of 2x, which would be the square root of 2 times 2ax. Now, here's the other way that you can figure out your velocity is going to increase by the square root of time. V equals v naught plus at. My initial velocity is 0. That's how one way I could have got my final velocity was just taking 9.8 meters per second squared times time. Well, if we just said that my time increases by the square root of 2, my velocity increases by the square root of 2. So that's the other way that you can look at it in terms of v equals v naught plus at. So here's my point. What I want you to see is that the more different ways you can look at these relationships, the deeper that understanding is going to be. Okay, so just don't get wrapped up in plugging numbers into the equation. Oh, right. Horizontally, there's no forces. Okay. Velocity stays constant. All right, no worries. Vertically, oh, right, we did acceleration. Why? Because there's a force. Okay. Do you think I'm ever going to give you the mass of the projectile?
Maybe to trick us.
I won't.
You did it on one of our papers. There was something in the information where we didn't need it.
Yeah, I did. But then I said, now, what would happen if you doubled the mass? And because I remember, it was like, on D I said, why didn't I give you the mass? He said, it doesn't matter. And the next question I said, okay, what's going to happen if I double the mass and I launch it at the same velocity? And what I wanted you to see was like, it doesn't matter. And some of you said, oh, it's not going to go as high because it has more mass. Like, no, for the love of God, you just told me that mass didn't matter. Yes, I remember that exactly. And I remember screaming in fits of rage. Okay, maybe not fits of rage, but definitely screaming.
You did it. So we
I
turn
did
it
what?
off.
Okay.
You need to give him his
All
tool
right.
back.
You're going to take yonder marble, you're going to hold it up like this, you're going to let it go, it's going to come down. We'll get into energy later. You're going to be storing potential energy. Mother Nature hates potential energy, so what's Mother Nature going to do? Change it into kinetic energy, because I promise you, if you let go of it, it stays there. Something weird is going on. Okay? The other way that you can look at it is Mother Nature is a lazy prima donna. Mother Nature wants this thing down at the bottom, not up there, because Mother Nature goes, that's a lot of work to hold that up there, quite frankly, I just don't care. So you're going to let go of it, it's going to roll down, okay? Then it's going to become horizontal. Then it's going to turn into a lemming, and then it's going to go out like this, okay? So you're here, boink,
Save the bird.
there you go. Now, here's the data that you're going to need to collect.
He committed suicide.
You're going to need to measure the height, okay? And then you're going to need to measure the horizontal distance. Now, to measure the horizontal distance so that we can get an accurate measurement, you're going to use carbon paper, okay? And carbon paper is kind of cool. So what you're going to do is you're going to roll it down once to get an idea about where it's going to land. Then you're going to take a piece of paper and tape. You don't have to like put all four sides, okay? But just secure that and then get an idea where it's going to land. And then put this piece of carbon paper over it. Put the diamond side up on top, okay? You're going to have two sides. The diamond side goes up on top. So then when it lands like this, what it does, it will transfer a mark onto this paper. So then you can measure the horizontal distance from here out to where it lands. So that's all the data that you're going to need. Why am I not going to put out a scale so you can measure the mass of the marble? Doesn't it?
Because you couldn't hook it onto the scale.
Huh?
Because you couldn't hook it onto the scale.
Well, it would be like a pan balance. We could do that. Yeah, that'd be tough to hook up to a Newton scale. It won't stay there. Work here, you jerk. Okay, so,
Like,
idiot. So anyway, so that's beyond. Well, beyond we can't measure it, and it just doesn't matter. So here's what you're going to do. So give that a spin. So you're going to have yonder ramp. Ball's going to come down. We're going to look at it from the perspective right as it leaves the ground. So all this analysis is starting from this point. When I ask you questions, I'm not talking about up here, okay? I'm talking about from when it leaves the ground, or when it leaves the ramp right here. And we're assuming that it's horizontal motion. You need the time. Do not ask me for a stopwatch. You're going to calculate the time, okay? Don't go, oh, well, time. No, you're going to calculate the time. So here's what you're going to know. You're going to know the range. So here's going to be your piece of paper, and you're going to measure that. You're going to measure that distance from the bottom, from the edge of that ramp, straight down. So you're going to measure that range, and then you're going to know that height. That's all the data that you need. And then you're going to calculate everything else from that. Now, what I want, oddly enough, show your work, because everybody's different. This is why I got this whole section over here for calculations. Okay, make sure you do that. What I want for that velocity resultant, what I want there is that when it lands, you're going to know Vx, and you're going to know the final velocity. So what I'm wanting is that resultant, and I want this angle right here. Don't worry about like subtracting that from 180 or from 360 and coming all the way around like this. Just give me this angle right here. Let's just make it simple. That's typically between around 70 to 80 degrees. Okay, if you do that right, that should typically be somewhere around 70 to 80 degrees. Like I said, don't worry about working all the way back to here. Just measure this, boom, there you go. There's your Vx, there's your Vy. Boink, there you go. Okay? All right, I am done. You're on your own.